Hello everybody, I am Ayush Prasad from the Funtastic Academy. Today, in episode 5 of Classical Mechanics, we're going to learn about work, power, and simple machines. Note that this is the last video in my playlist about classical mechanics. Okay, let us begin. Starting with last video quiz question. The quiz question from the Republican Special. Okay, so the quiz question was, what is a conductor and an insulator, and gives me some examples. Well, a conductor is a material that allows electricity to pass through it. But an insulator is a material that doesn't want electricity to pass through it. Some examples of conductors are copper, iron, and many other metals. Some examples of insulators are plastics. There's also glass. Pretty much anything that's not a conductor is an insulator, except for semiconductors, but that's a story for another video. Anyway, let's start talking about work. What is work? Scientists define work in a different way than normal people. Scientists define work as the amount of energy needed to move an object in the direction of the force applied on it. In the direction of the force applied on it. That's a very important point. Work is measured in joules, and work equals distance times force. That force is only the force in the same motion as the object. What in the world does that mean? Well, that means if you're doing this, carrying books around the house, it's not actually work. Why? Well, you're pushing the books forward, upward. You're acting a force on them to push them upward. But the books move forward because you're walking forward. So that cannot be counted as work. However, start moving upwards, presumably by going up the stairs, then you'll be moving upwards the books, and so the books will move upwards and that'll count as work. Okay, with that correctly, we can talk about power. Power is the rate at which work is done. It's how much work a machine can do in 1 second. Power is measured in watts. Power equals work divided by time. Okay? So now that we've talked about power, we can talk about simple machines. A machine is anything that makes work easier. You might think a machine as something complicated, like a computer or a car. In reality, a machine can be really simple. It just has to be something that makes work easier by increasing the distance you have to put the work over and thus decreasing the force. I'll be talking about the 6 different simplest machines today, starting with the ramp. Okay, so let's talk about the ramp. Say you wanted to move this eraser on top of this pile of books. Let's say you were about this small. Okay, so at that size, this would be almost impossible just lifting the eraser. The distance is so short, so you have to apply a huge amount of force to do the same amount of work. Unless you do this and make a ramp. Then the distance after ramp, as you can see, is much larger than the direct lifting distance, and thus you need less force to accomplish the same amount of work. Fun Egyptians actually used ramps when building the pyramid. I mean, the pyramids, because there were lots of them. But anyways, stairs are just ramps, just less smooth. And also, since they're just going up, sideways, up, sideways, up, sideways, they need less distance, therefore more force. So stairs are much less efficient than ramps. But still, steps or just direct ramps, they are machines. They decrease the amount of force you need to do the same amount of work. And this happens with all machines. The way scientists call a ramp is an inclined plane. Plane is something flat, like this book, and inclined means that it's not just laying flat, it's going upwards a bit as well. Okay, so now we've covered the ramp. Now we can go on to talking about screws. That's a very screwy topic, but we'll talk about them. Okay, so this is a screw. Now, screws are much harder to fit than nails. Let's say I'm using my finger as a nail and they want to fit through this board. So as a nail, you just need to push it and it will just go through. But since it's so low distance, they need a huge amount of force to do the same amount of work. Screws, on the other hand, they are basically just ramps, but they're going around at the same time. So they need much more distance, and thus, with much less force, you can do the same amount of work. By the way, technically, that spiral staircase in your grandpa's home is a screw because it's a ramp twisted around. One of the most famous examples of a screw is the Archimedean screw, which was basically a gigantic screw dunked in water with a hole at one end. Basically, the water would go up the screw when you turned the screw, and then it would go out the hole at the other end, and if you were a person with severe drought, it would water all your crops without having to take the bucket, put it in the water, take it out of the water, and pour it all over your crops. Okay, so now that we've covered screws, that's very screwy, we can go on to talk about pulleys. Okay, so let's talk about the pulleys. You know how they raise the flag at the Red Fort every Independence Day? But the flag is gigantic, the pole they raise it up is gigantic. How in the world do they raise it up? Using something called a pulley. What is a pulley? A pulley is just a wheel with a groove in it. And there's a rope wrapped around that groove. On one end of the rope, there's an object, definitely not the flag, and that object is going to be raised using the pulley. On the other end of the rope, you apply a force, and the end of the pulley with the object goes up. Okay, so that was a simple pulley, but more and more pulleys can join together to create double pulleys and triple pulleys. You can have basically an infinite amount of pulleys, and they can be used much more efficiently. See, because the rope is double the distance that you want to lift the object, you need half the work. So that was pulleys. Now So now, ladies and gentlemen, I shall present to you the lever! Okay, so maybe that was too much, maybe it wasn't, but here is a lever, also known to normal people as a seesaw. No, literally, a seesaw is just a lever made for fun purposes. Okay, so now a lever has three main parts. One, this ruler here, which is a bar, and that bar is gonna move around a fulcrum. A fulcrum is this eraser at any point where the bar, the ruler, can turn about. There's also the load and the effort. The load is the object that you want to move. The effort is the force. Okay, so to demonstrate, I have these 3 coins. They're pretty much the exact same coins, so there's no chance of a flip happening here. If I put one side down here on the 10, you can see that immediately sinks. For another side here at 20, it basically balances perfectly. If I put another coin on 20, it sinks. But here's something special. If I pull this coin to 5, it basically balances. So what's going on? This is because of Archimedes' principle of the lever. The principle of the lever states that the amount of up that goes on one side of the lever is equal to the distance from the fulcrum times the weight of the load. So one side had 2 times the weight and another side had 2 times the distance, so they balance each other out. Now, for one of the most familiar simple machines, the wheel. Okay, so everyone, meet Wheelie. He is a wheel. Okay, so that was probably all doing it like the lever. But anyways, so a wheel is one of the most commonly known simple machines. Now, the real name of wheels are wheels and axles. An axle is like a smaller wheel attached to a big wheel. If you see here closely, you can actually see this metal part here. That part is the axle. It's connected to the wheel. When the axle turns, the wheel turns. When the wheel turns, the axle turns. Okay, so there are 2 major ways wheels are used. One, they can be used to increase the force. See, if you turn the outer edges of the wheel, the inner parts of the wheel move slower, but they move with more force. They can also be used to increase the speed. If you rotate the inner parts of the wheel, the outer parts spin with much less force, but they go much faster. Despite the variety of rules, less force is faster and more force is slower. But that's how wheels work. It's much harder to turn the pencil to neck of a faucet than the actual tap. That's an example of a wheel increasing force. Also, by turning the pedals of your bike very slowly, you can be zooming across the street. That's an example of a wheel generating more speed. Okay, so that was the wheel. Finally, let's talk about the final simple machine, the wedge. Okay, so let's look at the scissor. A scissor is a wedge. Well, actually, a scissor is a combination of a wedge and a lever. If you look closely here, both of these halves of the scissor are levers. So it's a combination of a lever and a wedge. These combinations of simple machines are called compound machines, and they're what you usually think when you hear the word machine. Okay, but back to the wedge. The wedges are these bottom parts of these halves. The wedges are like ramps, but the difference from a normal ramp is that if you turn the wedge upside down, it's still a ramp. Because a wedge has to go much farther into whatever it's cutting, because it's perpendicular to the object it's cutting, it needs much more distance and thus much less force to do the same amount of work, just like basically every other simple machine. Now, to end things off with a bang, I'm gonna give you a real easy quiz question. Just name at least 4 simple machines. Of course, what simple machine you choose is optional, so the answers are gonna vary quite a lot. But still, name those simple machines, and I'll